Hi, welcome back to our lecture. Uh, that's our chapter 7, dealing with the probability, right? Living with the odds. Okay, the first section is the fundamental of probability. Right, so that's a couple of definitions before we see the actual work, right? So definitions need to be clear. Right, so the wording we will use: procedure. Procedures are the way we do the experiment, right? The thing, like flip a coin, rolling a dice or two dice or three dice, pick up cards or select subject, experimental subjects, and so on. A procedure is an action whose outcomes or results are random. Event, right? Any collection of outcomes of a procedure is an event. Like when you flip a coin 5 times, when you consider the number of time you get it ahead. When you're rolling a die, the event could be you get an even number, or the event could be you get an number greater than, you get a number that is at least 5, right? Or at most 3, something like that. Or when you pick up a card, right? If you know the card, that will be fine, right? If you don't know the card, how it look like, then we could find it, right? How that card is. Right, a procedure, whatever, right? Pick up a card, then like when you get a black card, right? Or when you get a spade card, right? Those kind of thing. Right, then sample space. Sample space is the set of all possible outcomes of a probability experiment. Like when you flip a coin, your result will be nothing else but only what? Head or tail to be the facing value. Right? When rolling a die, that will be one of the 6 faces, right? The usual one. And when you pick up a card, that will be one out of those 52 cards, right? So that 52 cards will be your outcome when you pick up one card. Equally likely event is the event that have same probability occurring. Right, so notations, we usually use capital English letters for the events, right? Event, if not specified, we could use the E letter. Some question will specify it. We could use A, B, C, Y, M, X thing, or whatever we can use, right? All the things we can use, the letters, or sometimes even subscript could be appear, right? PR of parenthesis E means the probability of event E occurring, right? Or probability of event E occurring. So that's how you write it. In your book, you may say P of E, but that thing will be a little bit confusion with the previous chapter's work, right? So, or later chapter's work. So we use PR. That's more commonly accepted in the world, right? Also. So just PR of E stands for probability of event E. Right. The approach we're going to use simply will be the classical approach. If a procedure has n simple events that occurs equally likely, and there are s different ways that event E occur, then the probability of E equals S over N. When we deal with this example, that'll be more easy, right, to see. The example here, rolling a die once, a fair die, I assume it's fair, the probability of getting an event in an even number. Right, so getting an even number, so probability of E, where the E is getting an even number. We just roll the die once, the die could be either facing value to be 1, 2, 3, 4, 5, or 6, right? So there are 6 different values. And what? And you want an even number, that's 2, 4, or 6, right? So you have 3 of the possible outcomes, right? So when you do your work, you need to show me the idea, what you're thinking, right? 3 over 6, that means that's 3 even number over 6 different outcome. Then you could either do simplification or to decimal, doesn't matter, right? But you have to show me this step. You could reduce to fraction, you could just divide to decimal. All right, let me find the outcomes for you. Courses over here. Right, so that thing actually shows you the deck of cards and what happens when you're rolling dice, right? You're rolling a die, usual one, that roll once you get 1, 2, 3, 4, 5, 6 as the outcome. And when you're rolling 2 dice, that's different pairs, and possibly will give you the sum, right, of different values. And when you have a deck of cards that different name, have from ace to the king, that's 13 cards. And the clubs and the spades are black cards. Heart and the diamonds are red cards. Each one of the 4 suits have 13 kind of cards from ace to 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, and king. Right, so that is how the outcome look like. How the outcome look like. Right, so other approaches for information only, that has relative frequency approach when you observe the procedure larger number of times and count the number of events that occur. Like when you rolling the die once, ideally you get 50% to get an even number. Maybe you do the relative frequency approach, you do larger number of times. For instance, you roll the die maybe 1,000,000 times. Then from that, you get, for instance, right? We could say that. Roll a die 1,000,000 times and get 499,958 heads. I mean, not a head. Even numbers. Right, then the likelihood will be just 499,958,000 over 1 million, right? Over 1 million. Well, that, of course, nobody gonna do the experiment that many times, right? So that's just an example. Don't take that too serious, right? When you do a question, you'll not be asked to do in the way of relative frequency approach. That takes too much time. Also, the subjective probability is the likelihood is found based on the knowledge of relevant circumstances. Right? So it is also just based on the knowledge, will not be that much accurate. The thing, ideally, what we use is just the classical approach in our course, right? So that 2 approach are just for information, right? You'll see, well, that's maybe other approaches possibly. Okay, so the two-way table is the first example we're gonna see, right? The most simple type of problem. Right, the two-way table here shows what? Shows, well, there are total 1,000 subjects in the drug screening test. And the results are here, right? Subjects, there are 44 subjects uses drugs and have positive test results. There are 90 subjects not using drug, but also have a positive test result. There are 6 subjects uses drugs, but have negative test results. There are 860 subjects who are not actually using drug and gets the negative test result, right? So these two, 44 is the true value. Those who are positive and use drugs, this is true value. 860 are those negative and not using drugs. This is also a true value. The other two are the errors, right? Those negative but actually uses drug. Those people not using, those subject not using drugs, but actually shows shows a positive result, right? So there are 134 positive result. There are 866 negative result. There are 50 who use drugs. There are 950 who not using drugs. So the row from column tells positive and negative. Total from column tells positive and negative. Total from the rows tells subject uses or not using drug. And there are 1,000 total people, right? Your row total, your column total should be same. And the total number is what you should find when you get the table first, right? In your work and in your homework and in your exam, we're not showing you the number in red and purple. You'll find it by yourself. That's your first step to do. Right, so when, the question now here, right? When one of the subject is randomly selected, what is the probability to get the subject has a positive test result? No matter using or not using drug, that's 134, right? So probability of positive test result is what? 134 positive test results possibly to be chosen out of those 100 subjects. Right? You want to reduce fraction, you want to divide it. That's either way you can do, right? If it's finite result, just keep it, right? 0.134. If it's infinite result, usually for the probability, I wish you to keep at least 3 or 4 digits of decimal. Right, so probability, the second question, right? If it's not a drug user, there are the row here, right? There's the row here that the subject is not a drug user. 90 has positive, 860 has negative, but total that's 950 of them are not drug user, and total of 100 result, right? 1,000 subject, right? That's 0.950, right? You could use always calculator to verify the result, right? 950 divided by 1,000, that's 0.95. 134 divided by 1,000, that's 0.134, right? Okay, so next question. Oh, the 2 boy and the 1 girl, right? What is the probability of getting 2 boys and 1 girl if a couple decide to have 3 children and assume they're equally likely, right? We'll see more reasonable thing on the later section, but here, right, that's a couple giving birth to 3 kids, right? So we have 3 steps, right? 3 kids. First, baby. Second, and the third, right? 3 newborn babies, right? Newborn kids, newborn children, right? No matter what happened, the first kid could be either a boy or a girl, right? That's for sure. Then if the first newborn is a boy, your second is not affected, and that's still equally likely to have a boy or a girl, right? That likelihood is still 50-50 chance, right? And if the first is a girl, then the second could also be a boy or a girl. And extend to the third column, that same idea. If the first two are boys, or first is a boy, second is a girl, that doesn't matter, right? The third kid could be boy or a girl, right? Also, if the first is girl, no matter second if it's a boy or a girl, the third could still be a boy or a girl, right? So that's all the possible combinations we have, right? Possible set we have, possible groups we have. And that first, second, third, they are like coming out different order, that matters, right? If the second is a girl, that is different than the third is a girl. The other two are boys, right? That's very different. So we have the total case, that's 3 are boys. First, 2 boys, and the third is a girl. First boy, second is a girl, and third to be a boy or girl, right? Then first is a girl, second to be a boy, or third to be a boy or girl. First is a girl, second is a girl, then the third could be either a girl, boy, or a girl, right? Yes, boy or a girl. So we see that for this procedure, that has 8 outcomes, right? That has 8 outcomes. And what we want is what? What the seeking probability is 2 boys and 1 girl. 2 boys and 1 girl. First and the third is a boy, the second is a girl, or the first is a girl, the second, third is a boy, right? That is, we can see all the possible events, possible ways the events can occur, right? Can occur. So we have what? The probability, wow. So the probability of this event, that is actually what? 3 cases possibly happen over 8 total outcomes. Right? If you want to convert to decimal, 3/8, that is 0.375. Or if you want to convert to percentage, that's even okay, right? 375, right? That's just finite decimal, just keep everything, right? Right, that's 2 boys and 1 girl case, right? The next one is the topic about the probability of an event not occurring. Right, so if the probability of the event E occurring is probability of E, then the probability of event not occurring is 1 minus it. Because 1, that means 100% occurs, right? So everything occurring is 100%. When the E occurring is probability of E, then the remaining likelihood will be it not occurring, right? Based on that idea. So not 2 boys. Oh, we find the probability of 2 boys and 1 girl to be 3/8. So what's the probability that the random chosen family with 3 children does not have 2 boys and 1 girl? Why not 2 boys and 1 girl? Right. So we find the probability of 2 boys and 1 girl in the last question, that's 3/8. So it's actually called complement, right? 1 minus it will be 1 minus 3/8. That is 5/8. And well, you can keep 5/8 as the final answer since that's the simplest, or you can convert to decimals, right? 5/8, that's 625, right? 0.625. All right, so that is this question. Right, so for the next question, you can actually try it, right? X denotes the face value of a die shows when it lands, when rolling a die once. And we have the outcome when rolling a die once, the outcomes are 1, 2, 3, 4, 5, or 6. Right? Just apparently very apparent, right? Very clear. So the likelihood to be it's even, that is what? Well, we have 3 numbers is even, so we have 2, 4, 6, right? 2, 4, 6 are even numbers. 2, 4, and 6 are even numbers out of 6 of them. That's what we have seen in the example already, right? 3/6, that's 1/2, that is 0.5. And of course, when you're talking about probability as odd, that's also 3 odd number, right? That's 0.5, but also, right, the probability as odd is the complement of x is even. Right, so when we get it, the likelihood of even is 0.5, we could just use it, right? You don't have to do a probability again, right? Just take away. And the next question about the outcome is 1, right? That's only one number to get outcome 1 out of those 6 numbers. Right, so that is simply just 1/6. And 1/6, 6, that is 0.16666 all the way. Round it, you can to usually 3 or 4 digits. I personally would prefer 4 digits, right? But don't keep less than 3, right? 4 digits will be good. Right? The likelihood to it to be greater than or equal to 2, that is actually not is equal 1, right? At least 2, that means the outcome is not 1. So exclude that the outcome is 1. Well, I'm always having a little trouble when writing the 6, right? Always looking not that good. Okay, that is what? 0.8333, right? 0.8. Oh, 10 subtract 1 minus 0.1667, that's 0.8333 to get the probability, right? Rolling one die. Right, the simple probability, you will see more practice in your homework, your homework assignment. The next topic is about the probability distribution. Right, the probability distribution represents the probability of all possible events. To make a table of the probability distribution, what you need is first, list all possible outcomes, use a table figure if it is possible, if it's helpful. Identify the outcome that represent the same event, find the probability of each event, then make a table which one column lists with each event, and another column lists with each probability. Right, the sum of all the probabilities must be 1. Right, so we do by example, we'll see what is that means. Right, so tossing 3 fair coins. I'll make a table of probability distribution of the number of head occur when 3 coins are toasted simultaneously, right? Simultaneously. So number of heads, right? So still, right, same as the newborn baby case, we have 3 coins, that's first, second, and the third. That's unbiased coin, right? So we have the first could be either head or tail, second could be head or tail, no matter what. Third could be head or tail, no matter what, right? No matter what. So we have the sample space usually represented by S, right? As a set, that's 3 heads, 2 heads and a tail, head, tail, and a head, head, tail, and a tail, tail, head, and head, tail, head, and tail. Last will be tail, tail, and the head, and the tail, tail, and the tail. Right, so we have what? Number of tails need to be considered. There are totally 1, 2, 3, 4, 5, 6, 7, 8 of the possible cases. And what? And totally 3 heads or 2 heads or 1 head are possible, right? So let's see. We want to build a table and the number of heads. That could be used the letter X to represent it. And its probability, right? So probability of X could be 0, could be 1, could be 2 or 3, right? The total of the number of heads doesn't make any sense, but the total probability we said should be 1, right? That's list all the possible outcomes, use a table of figures if it's helpful. Identify the outcome represent the same event, right? So that's first step we done. Identify the same event, right? So we use different color, right? And then let me use the red. Right, so for 0 head, that is only the tail, right? The 3 tails are there. Yellow. That 1 head, we have tail, tail, head, tail, head, tail, and head, tail, tail. That's 3 of them. Right, 2 of it. That we have 2 heads, 1 tail, 2 heads, 1 tail, and tail, head, head. And the last one, we have all 3 heads, right? I use different color, hopefully you can see it. All 3 tails, that means that means what? Let me use different color to put. All 3 tails, that means it's 0 head. That's 1 case out of those 8 cases, right? 1 out of the 8. 1 out of 8, that's 0.125. Right, 1 tail, I mean 1 head and 2 tail, that's put in yellow, right? 1 head and 2 tails, that's 3 cases. That's 0.375. 2 heads I put in blue, that's 2 head and 1 tail. That's 3 cases out of 8. That's 0.375. And finally, one case that has also all three heads. That's 1 out of 8. That's 0.125. Right? So that is the probability distribution, right? How to make it. Number of head, 1, 0, 1, 2, 3. Probability, we just double check, right? To see what is the total, right? Maybe use another color. Total, that's 0.125 plus 0.375. 375 plus 0.125, that is 1, right? Or even you can add the fraction to show the total is 1. Right, the total is 1. Right. Oh, wow. Here is the probability distribution when you're rolling the sum of 2 dice. Right, sum of 2 dice. Rolling sum of 2 dice, we have the outcome here. Right, both are 1, first is 1, second is 2, blah, 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 right? That's everything. If the first is 2, second could be 1, 2, 3, 4, 5, 6. If the first is 3, second could be 1, 2, 3, 4, 5, 6. All the way if the first is 6, the second could be 1, 2, 3, 4, 5, 6. Right, so that is the outcome of rolling 2 dice. So if we take the sum of the face value, if we take the sum of the face value, we will see the sums are 2, 3, 4, 5, 6, 7. 3, 4, 5, 6, 7, 8. Right? That's right, right? 3, 4, 5, 6, 7, 8. No, not 5. The first is 3, second is 1, that's 4, 5, 6, 7, 8, 9. 5, 6, 7, 8, 9, 10. 6, 7, 8, 9, 10, 11. And 7, 8, 9, 10, 11, and 12. Right, so we have that. And the likelihood, right here, we have the sum 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Right, so could make a table. This time will be longer, right? Have the sum representing, we could use the letter Y, right? And the probability of Y. Okay. So 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and finally 12, right? That's all the outcome we see, right? We see the sum 2, 3, all the way to 12. And kind of, well, we have 36 outcomes of the sum. From that, that's 1 only, right? Has 2. That's 2 of it has maybe I'm gonna erase the right side to put the decimals, right, for the likelihood. Yeah. Right, extend that each rows a little bit, that I will able to write down the decimal answer instead of the fraction, right? Additional to the fraction. And right, 1 out of 36, we could use a calculator right here. 1 out of 36, that's 0.0278. 2 out of 36, 0.0556. Here is not exact, so the answer is rounded, so maybe it will be a little off, right? The 4, there are 3 of them. 5, there are 4 of them. You can see from the left. 6, that's 5 of them. 7, that's 6 of them. And when you go to 8, the number getting decreased. You can see from the diagonal, that's only 5 of the 8. That's only 4 of the 9s. That's only 3 of the 10s. That's only 2 of the 11s. That's only 1 of the 12. Right, so on the bottom, we know that's 0.0278, and then we know that this one is 0.0556. Right, 3 out of 36, 0.08333. 4 out of 36, that's 0.1111. Right, even for that case, you leave it as a fraction, that's also a perfect idea, right? Good idea. 0.138888. 6 out of 36, that's 0.1667, right? And the 5, 4, and 3, and 2 and 1, right? The distribution. Well, the distribution can do other things, right? But that here is just the distribution, summarize your sum of 2 dice. All right, so that will be it for the fundamental probability, right? Thank you for watching. Thank you.